Thanks for checking out this quick video on AI and LLMs and RAG and all the other acronyms you can think of. I know it's not specific to Akka, but uh, if you are a developer and you even have the tiniest exposure to social media these days, then all you're seeing is just an onslaught of AI related news. So, what I thought I would do is go through some of the vocabulary and concepts that people are seeing today to hopefully give you some tools to at least decide, which rabbit holes you want to go down, which things you want to research, and which things you can, safely, follow from a distance, so to speak. So there's a bunch of terms and concepts that are involved in the type of AI news that we're seeing today. We've got vectors, embeddings, vector databases, vector distance, prompts, prompt engineering, RAG. So it may be a quick video, but I'm going to go through all of these. So the first thing is vectors. If we were to try and boil down all of AI to one key fundamental technology, then you'd probably have to say that it's vectors and vector math. And the standard mathematical definition of a vector is a line that has both magnitude and direction. So you can think of three-dimensional vector is some line pointing in 3 dimensions, and so I've got another two-dimensional vector here. The trick comes from when we try and get to vectors that have way more than 3 dimensions. Our tiny little brains have trouble visualizing what you know a vector looks like that has 4 or more dimensions. So the way I try and visualize it, and I know this isn't completely technically accurate, but the way I try and visualize it to at least give my brain something to latch onto is that I think of vectors as a path from one place to another. And so what I've got here is a vector that's going 3 units east. And so let's assume that this is some sort of a map, right? And there's very little information in this vector. I know where it started and I know where it ended, and it took a complete straight line to get there, and that line is a length of 3. So if I were to try and compare this vector to other vectors, I would have to say that the best I can do is determining whether one of those vectors is on this line or not on the line. But if I want more information about a path, maybe which side stops I took, which gas stations I stopped at, or whatever, I can add more information to this vector. And I've got wavy lines here, but that's just for an analogy here. So in this one, in this line, I can convey a little bit more information. I know where I started and I know where I finished, but I also know one point along the way that I took. And so now, if I want to compare this path with other paths, I have a little bit more information to go on. So I can tell the difference between two lines that ended up in the same place but took a different path. So if I extend that concept to many, many, many dimensions, I try and think of it like a route that had many different waypoints. I'm still starting and ending in the same place, but now I have a tremendous amount of information about what I did and how I took and what routes I took in order to get to the end. And in AI, these types of vectors are very similar, where I might have a vector that has 1,000 dimensions, and obviously our brains can't figure out what direction is a 1,000 dimension vector pointing. And so I'll get into some of the math, and hopefully not too much math, but I'll get into some of the reasons why this type of information is crucial. But it's safe to think of it just as think about these very high dimensional vectors as You can think of them as paths or map waypoints or GPS pins, whatever helps you kind of visualize it. And like I said, vectors are pretty much the key foundational data structure in AI. There's all sorts of math, and then there's all sorts of things that we put on top of vectors. But understanding that vectors is essentially the fuel that makes all this stuff go is pretty helpful. So the next thing that I want to talk about is embeddings, and embeddings are just another name for a specific type of a vector. And these embeddings are essentially taking your human input, your text, and turning it into a vector. And as I said, the vector is what all the AI code operates on. So if you want to ask an AI a question, you have to turn your question into an embedding vector. So let's say my prompt is, how can I make money with AI? So how do we turn this into an embedding? The first thing that happens is the string gets tokenized. So we split it up into tokens, which is usually words, but you also take note here that the question mark, the punctuation, is also a token here. So what do we do with the tokens? Next, we need to convert these tokens from the text tokens into numeric token IDs. And I've got the word vocabulary listed here because it's important to know that these token IDs are unique to the thing that produced the embedding. So these token IDs are that embedding model or that LLM model's vocabulary. So token ID 12 in this example here refers to the word how, and it will only do that in the one place that I got that embedding from. If I were to take these token IDs, from an OpenAI embedding and then use them somewhere else, I would essentially be sending gibberish to the model. So now, once we have the token IDs, we can create a vector for each of the token IDs. And this is, I think, where we lose a lot of people, because each of these tokens, think about how the analogy of a path, a long route as a vector. Let's think of the vector embedding for each token is essentially the very high information path that is taken to get to that word or that token. And in many cases, there's another step where the location of the word within the input prompt is also relevant. So not only do we know where the token is, so the endpoint, and we know the path taken to get there, but we can also uh, factor into our queries where that word is within the prompt. And so in many cases, what happens is the vector that was generated for that token, we add another vector to it that contains the vector that tells us where the token was within the prompt. So I'm not going to go through all of these, but the key takeaway here that I wanted to mention is that this is not just a few dimensions. So when when I create a vector embedding, in some cases I could have over 3,000 dimensions for a single token, and there's a lot of math involved and plenty of asterisks. But you can think of this as the more dimensions there are in your vector embedding, the higher chance there is of having a more meaningful result. Obviously there's exceptions, but in general, uh, higher dimension embeddings are better, but there's also trade-offs. So I mentioned the idea of a path and a destination. And so when LLMs and vector databases, which I'll talk about in a minute, do their calculations and their semantic search, they have what's called a distance function. And so they do these searches by comparing the distance between your input vector, which is now an embedding, and what's in the database. And so, things that are more or highly probable results will be a shorter distance. But as data scientists and as people that are building and hosting models, we need to keep in mind that there are a number of different ways to compute this distance, and that all has specific meaning. So in this diagram, you can see d as the Euclidean distance. And if I were to use that, I'm essentially comparing the endpoints of these vectors. And so that distance function ignores the path that was taken to get to that endpoint. And there's a ton of reasons why you want to use the endpoint distance. But then there are also reasons why you might want to use the cosine distance, which does take into account the sort of the direction that the vectors are pointing. And you will get matches based on vectors that are pointing in similar directions rather than vectors that are pointing that have ended at certain points. There are, more distance functions, but um, essentially every semantic search that you do is going to have some form of distance function. And picking the right distance function can have a pretty extreme impact on your results. So where do we put these vectors? Vector stores or vector databases are designed to hold high dimensional data, and these vectors are just massive long sequences of floating point numbers. So first thing we need is something that's optimized for storing and retrieving large piles of these floating point numbers. But we also need to be able to do searches and to be able to scan through these databases based on distance functions. And so this is where you have vector databases that do this for you. I think a lot of people are probably familiar with Chroma. Seems to be a pretty common choice for, especially when you're doing local debugging work. But then there are also vector indexes that can be added to, essentially non-vector databases. So Redis allows you to add a vector index. MongoDB Atlas has vector indexes built into it. And there's a plugin called PG Vector for Postgres that will allow you to have a vector index. And once something has a vector index and there's some code that knows how to use that vector index, you can now do semantic searches. And as you'll see in a second here, semantic search is a key piece of the retrieval augmented generation or RAG flows. So you saw that everything gets split up into tokens, and then the tokens become vectors. And one thing that I think everybody needs to be aware of is that pretty much all of these LLMs, I don't know of any exceptions, but they all sort of treat the unit of work as a token. And that has consequences because a lot of these models are not free, especially OpenAI. OpenAI, I think, currently has some of the most expensive per token charges. And so what will happen is it's very easy to write some code that will produce way more tokens than are necessary. And so token management and prompt optimization at the token level both become really important activities for when you're building code that consumes LLMs or interacts with them. So I've mentioned the word prompt a few times, and I want to talk about that as well because this one can be pretty subtle. Lots of times you'll see people talking about prompt engineering and building and sharing prompts, and the prompts are very, very important. They're essentially the input for LLMs, and so the prompts that the model sees are not the prompts that you enter. There's this thing called a system prompt, which wraps the prompt that you entered in more instructions, and those instructions are sometimes they're general purpose, like if you were talking to ChatGPT. Other times, those instructions are very specific. Like those instructions could contain game rules or hints on how questions should be answered. So if I enter how many R's are there in the word burrito as my prompt, then the first thing that's going to happen is you're going to see the model uh, will get a prompt that has this sort of a preamble where we're telling the model what role it's going to play. In this case, the role it's going to play is the role of a question answering agent. What tone it should use, and the important instruction that it'll use the included context to answer the questions and nothing else. And this kind of instruction helps reduce hallucinations, and hallucinations are a whole other topic. And so now with this preamble set up, we need the context. And so the context often goes, below the user's prompt in the real prompt. And so there's some context here about how delicious burritos are. But in a RAG flow or retrieval augmented generation, the context might be things like documents that pertain to a particular customer or to a particular topic. The context could contain, you know, data queried for a particular user, report histories, all sorts of stuff, and being able to fill that context with really valuable information can really change the way LLMs are used and how useful their answers get. So I mentioned RAGs and what those do, and the flow for so the general idea behind RAGs is that LLMs, the models themselves, are static. What they know today is all they know and all they will know. They're a closed system. LLMs also generally have general knowledge. They can't see enterprise data or product data. They can't perform domain specific actions. And there's an asterisk there because there's some gray area, but by and large, LLMs can do no work. So in a RAG flow, you're going to want to retrieve the context that's relevant to the particular prompt. And many times that context comes from doing a semantic search on, indexed data that you want to be available for prompt context. So the flow here is a user will talk to an AI agent or an AI agent service, depending on the terms you want to use. And the user will supply a prompt. The agent then does a lookup on conversation history. So, the history of the back and forth that you've had with the agent, so that in this conversation history, you can refer to things that the agent replied with before, and because that conversation history will end up as part of the context, the LLM knows how to respond to it. So we grab the conversation history, and then we do a semantic search against the vector database in order to pull, whatever other information we think is relevant to the question being asked. So, like I said, that can be, anything from publicly available documentation or code to, information that is specific to the customer that is involved in this particular agent session. And then the full prompt, which you saw a minute ago, that full prompt gets sent to the LLM, and then we get answers, and hopefully those answers are what we're looking for. So there's a bunch of words going around that are overloaded, as usual with most new things. Uh, Words and terms and categories all get overloaded, and these are my views of these words. I think everybody is likely to have a very different opinion, but when I think of agentic, I think of the English word agency, which means that you can act independently to achieve outcomes. And in an agentic flow or process or whatever you want to call it, that is stateful. So these agents have state, so they can remember what they've done in the past. And just kind of an aside here is that Akka has always been agentic in nature. The code that you build with Akka, whether it was on older versions or whether it's on the SDK that we use today, um, the things that you build are agentic. And then the only real difference between agentic and agentic AI is that agentic AI is agentic behavior that can utilize AI to achieve its goals. So Akka has a bit of a role to play here in the AI landscape, and a couple of reasons why Akka is so well positioned for this is that talking to LLMs is a stream. Tokens are streamed into the model, and then tokens are streamed out of the model as the response. And so, whatever you do that is going to communicate with these LLMs needs to be streaming as well. The agents, whether they're using AI or not, are stateful. Here, you need to manage session memory, conversation history, workflows that need to be orchestrated. And another way to think about it in an event sourced term is that interacting with an LLM produces side effects or just effects. Another common activity is prompt caching. Like I said, depending on what you're using, you could be getting charged per token or per million tokens or whatever. And so you might actually be paying money every time you generate an embedding to be used in a prompt. And so activities like prompt caching end up being not just beneficial for performance, but can turn out to be pretty big money savers as well. And we also, on the topic of money, we want to be able to meter the way these agents talk to LLMs. And so we want to do things like track and control token usage, API calls, tool usage, conversation history, the conversation history length, all of that stuff. And all of those are things that just sort of fit nicely into state in Akka's entities and workflows. So, what do you do next? The next thing I would say is I think the most important thing to do is not get distracted. Every single day, there are new things, new topics that come up. People are posting about these brand new revolutionary things that are 10 times better than they were last week. And trying to stay ahead of that wave is exhausting. And so, hopefully, with what I've covered in this video, you got a little bit more of an idea of the things that you want to pay attention to and the things that you can sort of pay attention to from afar or even ignore. There's a couple of really good books. Many of them that I found are really, really detailed. A lot of them are designed for people who actually want to know about the math involved, and not everybody needs to know how the math works. Hugging Face is like a child's toy box full of all kinds of stuff that we can play with. You can find data sets there. You can find llama models, which are LLMs that you can essentially run on your workstation. All kinds of stuff. I could waste years just playing with the stuff that Hugging Face has. Um, you can do some more research on vector databases, indexing, and prompt engineering. I think prompt engineering is going to be a really big thing going forward, because in many cases, the prompt is going to be the key thing that differentiates uh, one service or one agent from another. And then another one is, you could go into OpenAI, create an account, and then with whatever tool you feel like, start using the OpenAI API to see what it looks like to run prompts through it, and to see the real prompts and not just the prompts that you enter in the applications. And so that's all I had. I think in order to keep this short, I'm not going to go into detail on MCP, the Model Context Protocol. I might just do another video on that, since that's both a highly volatile topic, and there's more to it than just a few seconds. So stay tuned for more videos. Thanks for watching.